Welcome. Today we're going to look at solving trig equations. This is chapter 5.3 in your text. Let's go ahead and get our notes out and we'll get going. Remember, during the video, if you are struggling to keep up with your notes, make sure you pause the video, or if you didn't quite understand something the first time, stop the video, rewind it, and listen to that piece again. Sometimes it takes a couple times through to understand the concept. Okay, our objective for part 1 is students will solve trig equations with one trig function using inverse properties. If you recall, when we first introduced trig functions, we figured out our trig functions were periodic. Periodic simply means they repeat their pattern over a fixed interval or period. So, when solving trig equations, that means if we found a set of answers within a period and the period repeats itself, those same set of answers will be in every other period. This translates to that our trig equations can have up to infinity answers. Okay, let's go ahead and take a look at our first example. This is explain 1. Our example problem we're going to solve is 2 secant x minus 4 is equal to 0. Now, when solving trig equations, we're going to handle them the same way we would solve linear equations. Since this is a power of 1, we're going to use inverse operation to isolate not x, but isolate the trig function itself. So in this case, we're going to try to isolate secant x. So here we go. So to isolate secant x, the first thing I'm going to do is I'm going to move the 4 to the other side. I'm going to go ahead and use inverse property, so I'm going to add 4 to both sides. And that's going to leave me 2 secant x is equal to 4. Then I'm going to divide both sides by 2, and that will isolate our secant x on the left side, and when I simplify the right side, I will get 2. Now we're ready to find the angle, or solve for x, that when I take the secant of, I get 2. Alright, in order to find the angle needed, we're going to use our unit circle. So go ahead and pause the video and pull out your unit circle. Once you're ready to go ahead and restart the video and we'll continue on. Okay, to solve for x, the first thing we need to do is probably look at the reciprocal functions. This will make it easier to find the value or the angle on the unit circle needed. So what I'm going to do is I'm going to take the reciprocal of secant, which is cosine, and the reciprocal of 2, which is 1/2. Now go ahead and pause the video and use your unit circle to find where cosine is positive 1/2. Once you've found the angle or angles, there could be more than one, start the video and we'll see how you did. Okay, using your unit circle, you should have come up with pi over 3, which is our quadrant 1. Cosine is positive in quadrant 1. Cosine is also positive in quadrant 4. And we were looking for the pi over 3 in quadrant 4, which is 5 pi over 3. These are two solutions that when we plug in either equation will make them true. Now remember, secant is periodic. That means it's going to keep repeating itself. Therefore, I have to look at other periods. In order to get all infinity answers, what I'm going to have to use is the concept of terminal angles. Sorry, I said terminal, excuse me, I meant coterminal. We use the concept of coterminal angles. So I'm going to take pi over 3, and to represent all the other solutions in all the other periods, I'm going to add 2 pi. If I add 2 pi, I'll get to the next period. I'll be right there at the same answer. And because there's multiple periods, I'm going to say 2 pi n. N represents the number of 2 pi's I'm going to add or subtract to pi over 3 to get to my other answers. I'm going to go ahead and do the same thing with 5 pi over 3. I'm going to go ahead and add 2 pi n. And these represent all my solutions to where secant x is equal to 2. I can see taking a look at the problem we just solved graphically, we might get a better understanding of adding, or why we have to add 2 pi n to get all infinity answers. So here's a graph of 2 secant x minus 4. We can see our answers, or solutions, are the x-intercepts. So we have one here we found at pi over 3, and we have one here we found at 5 pi over 3. Now, if we think about the next period or cycle, we can see, or even just look at the x-intercepts, we can see that we have solutions here, here, here. Now we found those two. We have one here, here, and here, and we can keep lining them up. What we have to see or realize is these are exactly 2 pi apart. So this is my pi over 3, and I add 2 pi to it, I end up here. If I add another 2 pi to it, I end up here. If I subtract 2 pi from it, I end up here. And the same can be done with our 5 pi over 3. If I add 2 pi to it, I hit another solution. If I add 2 pi more, now you can't see him, but he's going to exist over here off my page. If I subtract 2 pi from it, I end up here. Subtract another 2 pi from it, I end up here. So you can see that we can get all our infinity answers represented by using or adding on just the piece 2 pi n to the two angles that we found. When we do this, this is known as our general solution. Okay, let's go ahead and look at another example. This is explain number 2, and we're going to find all the solutions of sine x plus the square root of 2 is equal to negative sine x in the interval of 0 to 2 pi. Now this one, unlike the last one, has an interval. So we just want the answers that exist between 0 and 2 pi. And if we think about that, that is one revolution around the unit circle. So unlike the last problem, we don't have to find all infinity answers. We don't need the 2 pi n tagged onto our solutions we find. We simply just need to find every solution one revolution around the unit circle. All right, let's go ahead and get started. So I'm going to write the problem down. I have sine x plus the square root of 2 is equal to negative sine of x. Now, just like linear equations, when I have variables on both sides, I have to move them all to one side. I'm going to do the same thing for this problem. To isolate the sine x, or the trig function, I have to move them to one side. So I'm going to go ahead and move the sine x on the left side over to the right by subtracting sine x from both sides. Whoa, new technology. Here we go. Let me kind of move that back. There we go. Bear with me, it is new to, or using the system is new, so I'm going to make a little bit of mistakes. So sine x minus sine x is 0, and I'm left with the square root of 2 is equal to negative 2 sine of x. Now to isolate, I'm going to go ahead and divide by negative 2, and I'm left with negative square roots of 2 over 2 is equal to sine x. Now our goal from here is to find all the angles between 0 and 2 pi that when I take the sine of, I get negative square root of 2 over 2. Okay, so to go ahead and take out your unit circle, pause the video, and find all the angles that when I take the sine of, I get negative square root of 2 over 2. Okay, hopefully the angles you found is x. Now the square root of 2 over 2, that is a pi over 4 angle, so we know everything's over 4. We know sine, which is also our y values, remember sine is y. Sine is negative in quadrants 3 and quadrants 4. So in quadrant 3, our pi over 4 angle would be 5 pi over 4. And in quadrant 4, it would be 7 pi over 4. Now these are the only two answers because our interval, remember, goes between 0 and 2 pi. Okay, before we move on to our last example, we need to answer the following question in your notes. So here's our first checking for understanding. It says, why do we initially only have two answers when we solved and not infinitely many? So referring to the last example we only had two answers, whereas the first example we had infinitely many. How do we know when we want two versus infinitely many? Go ahead and answer that in your notes. While you do this, pause the video, and when you're done, go ahead and turn the video back on. Okay, I'm going to answer the question quickly. We initially only have two answers when we solve this example because we were given the interval. And we were given the interval, we were looking for all the answers that were between 0 and 2 pi. So that, if you think about that, that is one time around the unit circle, and we only had two spots where the answer was true, or two angles where the answer was true. The first example, we were not given an interval, therefore it wanted all infinity answers. So we had to represent them all, and we use that with the 2 pi in, which represents coterminal angles. Okay, let's go ahead and do our final example. All right, our final example, we're going to solve 3 tangent squared x minus 1 is equal to 0. That's 3 tangent squared x minus 1 is equal to 0. So let's go ahead and write that down. As we write it down, first notice that this is our first example that's not linear. We actually have a quadratic here. But we're still going to use inverse properties to solve. In our upcoming videos, we're going to learn about factoring and quadratic formula. But because this doesn't have a linear term or a term with just one power, we can use a technique of isolating the trig function and square rooting both sides. So here we go. So our first step is to isolate our trig function. So I'm going to go ahead and add 1 to both sides. And we can see that I'm left with 3 tangent squared x is equal to positive 1. Now I'm going to go ahead and divide through by the 3, and I'm left with tangent squared x is equal to 1 over 3. Now to finish solving, to isolate the tangent, the trig function, I'm going to have to square root both sides. So in doing so, I'm going to go ahead and use a different color in here. I'm simply going to square root both of these. So that leaves us with tan of x is equal to, now remember, when solving by square rooting both sides, you absolutely must have plus or minus. And when I square root a fraction, it's square rooting the numerator. So this is the square root of 1 over the square root of 3. Now, to simplify it further, I can say this is plus or minus the square root of 1 over the square root of 3. Now, the square root of 1 is simply 1, and I'm left with 1 over the square roots of 3. Now, in the past, we would rationalize, but we're not going to rationalize this one because our next step is to figure out tangent of what angle is 1 over the square root of 3, which means tangent by definition is sine over cosine, or y over x. We're going to have to figure out, by looking at a unit circle, what two, or which x and y do I divide to get 1 over the square root of 3. Okay, go ahead and pause the video and take a look at your unit circle and try to figure out the angles that when you divide the y over x, you get 1 over the square root of 3. Okay, did you find your angles? No worries if you did. I'm going to show you how I approach this problem. So when I look at this problem, the first thing that I notice is we are 1 over the square root of 3, and there's a square root of 3 in the denominator. That tells me that my coordinates are the square root of 3 over 2 and 1/2. These these set of coordinates are associated with pi over 3's and pi over 6's depending on the order. So what I'm going to do is I'm going to try to figure out which order they divided, and that'll tell me which angle it came from. Now I look and see, because the square root of 3 is in the denominator, I'm going to take the square root of 3 over 2 and I'm going to put them in the denominator. My numerator is going to be 1/2. So when I invert and multiply, I'll get 1/2 times 2 over the square root of 3. I can see the 2's go away or cancel out, and I'm left with 1 over the square root of 3. So this is the order in which I have to divide, which tells me, using the definition of tangent, which is sine over cosine, or y over x, my y value would be my y value would be 1/2, and my x value, let me make that a little change color, would be the square root of 3 over 2. So in the order in which I wrote them up here is actually the order they end up being. These two coordinates are associated with my pi over 6. So if I think about my pi over 6 angles, and tangent was plus or minus, I'm looking for everywhere where tangent, or every pi over 6 angle that is both positive and negative. That's all the quadrants. So I'm going to go ahead and list them. In quadrant 1, it was pi over 6. Tangent is positive there. In quadrant 2, it is 5 pi over 6. And tangent is negative over there because sine and cosine have opposite signs. In quadrant 3, it is 7 pi over 6. And tangent is positive there. And in quadrant 4, let me back up. In quadrant 3, it's positive there because both sine and cosine are negative. And when you divide a negative, or two negatives, you get a positive. And lastly, in quadrant 4, that is 11 pi over 6. And that is where tangent is negative, because in that quadrant, the signs are different. All right, so these are 4 possible answers. Remember, tangent is periodic, and it's going to repeat itself, and there was no interval, so I have to get all the answers. Now, these are all my answers from 0 to 2 pi, or 1 revolution around the unit circle. However, tangent is different in terms of period than sine and cosine, or secant and cosecant. Tangent, like cotangent, has a period of pi. So I'm going to do the same thing that I did with the previous problem. To get all infinity answers, I'm going to take pi over 6, but I'm going to add pi this time because it repeats itself every pi. I'm going to take 5 pi over 6. I'm going to add pi over n, remember coterminal, because it repeats itself every pi, or its period is pi. Now these bottom two, the bottom two answers, the 7 pi over 6 and 11 pi over 6, while they are in 1 revolution of the unit circle, they are in a different period. If I were to add a pi to pi over 6, I get 7 pi over 6. One more time, if I add pi to pi over 6, I get 7 pi over 6. So I don't really need this one since he's already in this interval. 6 pi over 6, which is pi, plus pi over 6 is 7 pi over 6. So adding 1 pi would get me there. Same thing's going to happen to 11 pi. So if I look at where tangent's negative, that's 5 pi over 6. I add pi to it, I will get 11 pi over 6. So I don't need this one as well. So with tangent and cotangent, in this case tangent, our period is pi, so we use pi n and not 2 pi n as we did with sine and cosine. Now that we've seen 3 examples, let's go ahead and try to see if we can use the techniques. we have 6 example problems, numbers 11 through 16. Go ahead and give them a try. You can also find these problems on the presentation. Try them first. I will give you solutions, then take a look at the solutions after you've struggled a little bit and check your answers, or look back and see what you need to do to get from where you stopped at to the final answer. All right, I hope the video helps, and if you have any questions, feel free to email me. Thank you for listening.